All right, so where we were at the last 2 days, we're basically looking at the two options when we're looking at probability and trying to organize all the different things that could happen, the sample space. Okay, so 2 days ago we looked at an area model, and we said as long as you've only got two events, two things that are happening, area model will work. Yesterday we introduced a tree diagram that said if you have more than two, or even if you don't like the area model, you have another option. You can use the tree diagram, and you can organize it in a different way and answer the questions that way. Okay? Today's lesson, 423, for the most part, is kind of just picking when do I use which one, and it's more of like almost like a practice day, where we're going to work our way through it some more and just try to get better at it today versus something new. Tomorrow we'll go into kind of the next new lesson. There's for this stuff, for the chapter, for the 4-2s, the probability stuff, there's really only 2 lessons left for that. Tomorrow will be kind of a new concept, and then Monday and Tuesday we're going to take 2 days on the final one, but that's the last probability lesson, and then we'll go into the next stuff after that. Okay, so this 4-2-2 assignment is, so 4-2-1 is due today, by the way. If you haven't done the first assignment yet, that's due by today for full credit still. 4-2-2 then is due by tomorrow, and since we're doing 4-2-3 today, that will be due by Friday. Okay, those will be the 3 assignments this week that you'll need to make sure you get done, and then obviously the Delta Math is there over the course of the week as well. Okay, let's take a look at this one though. Problem 469 here. Eddie is arguing with Tana about the probability of flipping 3 coins. They decide to flip a penny, a nickel, and a dime. Not that it really matters, to be honest, that they're a penny, a nickel, and a dime. That's just their way of saying they're 3 different coins. You could be flipping 3 dimes and still get the same outcomes. Okay, 3 quarters, doesn't really matter. So first part, notice it says which one would be better for determining the sample space, a tree diagram or an area model? What do you think? What do you think? Tree diagram or area model, since we're dealing with 3 coins? Tree. Why do you say tree, Juliana? You're right, by the way. Okay, yeah, there's more than 2 things. We're looking at 3 different things, 3 different coins, which means we've got to use a tree diagram. Okay, so that's the first part. So part A would be a tree diagram because there's 3 things that we're working with. So then in part B, when they say make a sample space, what they're saying is either create, if you would have said area model, create the area model, create the tree diagram. Let's look at everything that could happen. This is the part that usually students struggle with, is trying to create the tree diagram. Not quite sure where the branches go, that kind of stuff. So here's the guidance I'm going to give you today. As you go through and we talk about this, think about the outcomes. It's going to happen in stages. So they said penny, nickel, and dime. Like I told you, it really doesn't matter whether it's a penny, nickel, or dime, or if it's a penny, penny, and a penny. It's still 3 coins is all that really matters, because you have the same outcomes on any coin. There's heads or tails, regardless of what the coin is. That's the part that you need in order to create the tree diagram. Okay, so if we take a look, here's where we're going to start. You flip the first coin. What are the outcomes? What could happen? Only 2 options. Heads or tails. Okay, those are the first branches. That's what's happening. So we'll start right here. Heads, tails. Okay, could be heads, could be tails. That's option number 1. Okay, then from there, we go to the second phase of this. You flip the second coin. What could happen? Come on, don't overthink this one here.
Tails or heads?
Thank you. Not here. So second coin, same thing, heads or tails. And so here's the idea. If the first coin was a head, you still have 2 options off of that. Heads or tails. You still have, if the first coin was a tail, you still have 2 options off of that. Heads or tails. Okay? So there's coin number 1 and coin number 2. Now we got to add coin number 3. And from there, once again, you still have heads or tails as an option. So regardless of if the first one was a head and the second one was a head, Third one still could be heads or tails. Okay? So again, off of each of these, you're going to also have two options. All right, so now there's basically the tree diagram. Now we're going to put together the final outcomes and the different things that could happen with the corresponding probabilities. Okay, I'm going to do that in a different color so it's a little bit kind of stands out. So option number one, if you just start following the branches, head, head, head. You could have 3 heads. Okay, and if you think about it in terms of this, I'll put the probability right next to it. If you think about it in terms of what's the probability of heads versus tails? 1/2 versus 1/2, right? Every single one of these branches has a 1/2 on it. Okay? I didn't put it in there just because I didn't want it to get overly cluttered, but every single one of these branches would have a 1/2. So what's the probability of 3 heads? 1/2 times 1/2 times 1/2. Okay? Which means you get 1/8 is the probability. If we go through next option, we could have a head, and then a tail. There's option number 2. Also, 1/8 probability of that happening. By the way, let me skip over here, see if you're starting to get this. How many total outcomes are there? How many will there be? There's going to be 8. There's going to be 8 things. We're going to end up with 8 total possibilities. That's kind of why these are out of 1/8. Here we could have head, tail, head. There's option 3. You could have head, tail, tail. Option 4. And then we go to the bottom half of the tree diagram. Could have a tail and then 2 heads. Could have a tail, head, tail. Tail, tail, head. And finally, all 3 could be tails. There's your 8 possible things that could happen when you flip any 3 coins. Again, regardless of whether it's a penny, a nickel, or a dime. Any 3 coins, you end up with 8 options, 8 things that could end. Those are the 8 different combinations, if you will. Now, here's why, and I know it's kind of a lot of work. It's not a lot of work, but there's kind of a lot going on there. Here's why it's worth it. Now it's just sitting right there, and now it's much easier to answer part C with all of this information sitting right here for you. So now if we take a look, they say find the probability of each of the following events occurring. Well, what's the probability that you have all 3 heads? Well, there's only one of those out of a total of 8 possibilities. 1 out of 8. That one's done. Then we go to part number 2. What's the probability that you end up with 1 head and 2 tails? Notice, order in this case doesn't matter. All you're looking at is how many of these have 1 head and 2 tails. So if we take a look, here's one right here. There's a head and 2 tails. Here's another one right here. Tail, head, tail. And there's a third one right here. 2 tails and then a head. That ends up being 3 different combinations that only have one head and 2 tails in them, out of 8 possibilities. Okay? 3 out of 8. The 3, if you can't quite see it, here's the 3. We say 1 head. There's 1. There's 2. There's 3. There's your 3 out of the 8. Okay. Now, get rid of that. Now, it says at least 1 tail. You gotta be careful about the wording on this one. At least means 1 or more. So now you're looking at all 8 combinations and saying, all right, which ones have 1 or more tails in them? So same idea. If we take a look, here's 1. Here's 1. There's 1. There's 1. There's 1. There's 1. There's 1. Answer? 7 out of 8. Okay? 7 out of 8 have at least 1 tail. The only one that doesn't is the 3 heads. That's the only one that doesn't have that. So in this case, we've got 7 out of 8. And now to finish up the last part with this one, exactly 2 tails. So now we're taking a look at, again, we're looking at our sample space here and saying, all right, how many of these have exactly 2 tails? Doesn't matter the order that they arrived in, just that they have 2 tails. So if we take a look, here's 1, here's 2, there's 3. Have exactly 2 tails. So once again, we're at 3 out of 8. And like I said, hopefully you're recognizing that it's a lot easier once you've got the final outcome sitting there with the tree diagram to answer the questions. Without it, you're kind of just guessing a little bit. You're trying to picture it or imagine it or something along those lines, and it makes it kind of difficult. Okay? Then when you get down to part D, they say which is more likely, flipping at least 2 heads or at least 2 tails. So even that, we can go back and we can kind of take a look. At least 2 heads, that means 2 or 3. So we've got, there's 1, there's 2, there's 3, there's 4. So 4 of them have at least 2 heads. And if you look at the other ones, 2 tails, 2 tails, 2 tails, at least 2 tails. So it turns out that they're both, in this case, they're both 4 out of 8. So they're equally likely outcomes on those 2. Flipping at least 2 heads has the exact same probability as flipping at least 2 tails. All right, the only thing left then, and this one gets a little bit confusing. Now they go into part E, and they say, how would their probabilities change if Tana found out that Eddie was using a weighted coin, a trick coin, if you will, okay? So that the probability of getting heads on each coin was actually 4/5 instead of 1/2. Okay? So as you're using a trick coin and flipping that coin, if it's weighted, 4 out of every 5 times rather than 1 out of every 2, you end up with heads instead. I'm not going to necessarily go back and finish this all out, but here's how we would go back and do it. If we go back to the tree diagram, and we put in the actual probabilities, we can recalculate. If this is 4/5, that you end up with flipping a heads, what's the probability of a tail on that coin? On the weighted coin. If 4/5 is heads, what's left? 1/5. So that means you'd have a 1/5 probability of getting a tail. And then same thing as you work your way through the tree diagram. Here you would have 4/5 for heads, 1/5 for tails. 4/5 for heads, 1/5 for tails. And you'd have to then go through and re-multiply your probabilities to calculate these final probabilities again. The outcomes would be the same, but the probability of those outcomes would then change. Okay? For example, we'll do one of them together. For example, get rid of this. If we were trying to calculate all 3 of them landing heads for this weighted coin, we would multiply 4/5 times 4/5 times 4/5. Remember when you multiply fractions? All the numerators, all the denominators. Okay? So 4 times 4 is 16. 16 times 4 is 64. 5 times 5 is 25. Times 5 is 125. So now the weighted coin, the probability of all 3 landing heads would actually be 64 out of 125. 64 out of 125. And then, like I said, same thing, you'd have to work your way through for the head-tail. You would go 4/5 times 4/5 times 1/5 and calculate that probability. And work your way through the whole rest of it to just basically recalculating the probabilities is all. Okay? Then you can go through and answer your final questions. Okay? How we doing? Making some sense? I know it's probably not 100% clear because in general, tree diagrams are a little bit harder to understand than area models are. But that's kind of that's the idea, at least, of what's going on. As long as we're here, does anybody else have any other questions that you want to go over on this assignment? I think most of it The rest of it is fairly straightforward, but any other questions from the assignment that you wanna go over? Okay, so here's what I want to do. So we're gonna get into 4-2-3 today, which I'm gonna skip some of the beginning stuff. I kind of changed my mind after I put it together. But 4-2-3, we are basically talking about which one should I use when, or can I use either? You know, those kind of things. It's basically, like I said, kind of a practice day. So if we go through to the first problem that I gave you in the note sheet, problem 476. So go to that next. Let's go to the notes. And I think I'll help you a little bit on this first one. We'll get you started, and then I'm gonna let you go through and figure out kind of the rest from there. So notice, there's a new game at the school fair called Pick a Tile, in which the player reaches into two bags, chooses one square tile and one circular tile. The bag with squares contains 3 yellow, 1 blue, and 2 red squares. The bag with circles contains 1 yellow, or has 1 yellow and 2 red circles. In order to win the game, in a large stuffed animal, a player must choose 1 blue square and 1 red circle. Since it costs $2 to play the game, Marty and Jerry decide to calculate the probability of winning before they decide to play. Okay, so they're trying to do the calculations and say, you know, is this game is this fair, or do I have really no chance of winning this game, and therefore I don't want to lose the $2 and throw that money away. That's what they're trying to figure out. So notice it says Jerry suggested making a systematic list of all possible color combinations. So Jerry says the answer is 1/6. So if you notice, here's where we're at. Okay? 1/6. Is Jerry right? Marty says that doesn't seem right. There's more yellow squares than blue ones. I don't think the chance of getting a yellow square and a red circle should be the same. What do we think? Let me go back to let me highlight a couple of things so that you have it, so you can see it quickly. The bag with squares contains, there's what that contains. And the bag with circles has that. There's kind of the highlighted information. What do you think? Is this a decent systematic list, or is there something wrong with this? Give me an answer here. What do you think? Is Jerry okay, or is Marty right? Because something's not right here. What do you think, Nick? What do you think?
I think it's right.
Okay. Do you think that the list is okay? Red and yellow, blue and yellow?
Oh, wait. No, not the other one.
The other one. Okay.
Yeah, sorry.
Why? Why do you go that route?
Because there's more in the first bag than there is in the second bag, and that's easy to really like.
That's exactly the right reasoning. Okay. The reasoning behind it is, yeah, you can put together the color combination, but there's not just one of each in there. So we have to account for that. That's going to change the probability. Okay. We can't just go on the colors. We have to also go with how many of those there are actually in the bag. So notice what they want you to do is they want you to make a tree diagram for the situation, and then we'll put the probabilities in, and that's where we can account for there being more than one. Okay? So here's where most people struggle. What I want you to do, and what I want you to think of is for the tree diagram, you have to think of tree diagrams as stages. Okay? So stage number 1 here is he's going to reach into the bag that has squares. What could happen? When he reaches into the square bag, what could be the result? What's he going to pick? Golden, what do you think? What could happen if he reaches into the bag of squares?
It's yellow, blue, and red.
There's your first part of your tree diagram right there. Okay, the first thing he's doing is reaching into that bag, and what could happen? You could end up with a red. Let's see, a little red. He could end up with a blue, or he could end up with a, what was it, yellow? Is that the last one? Yeah. Now you can make that a whole lot bigger. All right. So here's basically like bag number 1. I'm going to kind of label that stage, if you will. There's bag number 1. Now he's going to reach into the other bag. What could happen? What are the outcomes? What's the possibilities when he reaches into the circle bag? He's got not yellow, blue, or red. He's got either just yellow or red circles in that one. Okay, so there's 3 options in the first one. There's only 2 options in the second one. So in this case, from here then, could be yellow or red. From here, could be yellow or red. And from here, yellow or red. This is kind of representing bag number 2. I can't spell bag. BG, there you go. Bag number 2. All right. Now, let me ask you the question, because I'm going to go back to what Nick had said. He said earlier that it didn't seem quite right that we just had the different combinations. Because notice, that's pretty much what we now have in a tree diagram. We've got, first one could be red, second one could be yellow. Red, yellow. Then we could have red, red. That's an option. We could have blue, yellow. If we start writing all of our different combinations down. Blue, red. 2 yellows. Or a yellow and a red. And that list of 6 different things is exactly what we had up above. How do I now adjust it so for the number of things in there? What can I add to this? For example, we said that in this first one it could be a red square. Okay. If I go back to what we have, what's the probability you grab a red square? What's the probability that you end up with a red square from the first bag? Was it? Yeah, there's 2 red squares. There's 6 total in there. Okay, there's 3 yellow, 1 blue, and 2 red. The probability is where we're going to take into account the numbers. Okay, so in this case, if I put the corresponding probability, a red square has a 2 out of 6 probability. If you want to reduce it to 1/3, that's fine. You can. I'm going to leave it as 2/6 for now. Blue, we have only 1 blue square. Again, still out of 6 shapes. And a yellow one, we have 3 yellow out of 6. 3 out of 6 yellow. So that takes care of bag number 1. Now we reach into the circles. And in this case, there's only 1 yellow circle out of 3 circles. There's 2 red out of 3 circles. So it's either 1/3 or 2/3, depending on the color. 1/3 for yellow. We can put that in parentheses. 2/3 for red. And here's what I want you to do then. Okay? There's the tree diagram, bag number 1, bag number 2. What I want you to do right now, I'm going to give you just a few minutes to do it, is calculate the final probabilities then. Multiply the fractions together, get your final probabilities for each one of these final outcomes here. Okay? Go ahead and do that right now. I'm going to come around. If you get stuck, I'll help you out, and we'll go from there. Okay? Calculate your final probabilities.
That's all I got.
Right? I don't know why. Cold?
It's comfortable.
Fine.
How do you calculate it? Probability that in parentheses there. And you just like, and then you know, just gonna multiply the factors together. Oh, okay. And then you can find the probability.
And then you find the probabilities of the next step. So these are
So you mentioned it probability.
Remember when you multiply fractions, top times top, bottom times bottom. Alright, so here's the probabilities. Take a look up on the screen here. In green, I put the final probabilities down where you're just multiplying. So for the first one, for example, that 2/18 is coming from 2/6 times 1/3. Numerator times numerator, that's where the 2 is coming from. Denominator times denominator, that's where the 18 is coming from. And then just do that along each one of the different branches of the tree diagram. Okay, so now here's the question. Find the probability of a player choosing the winning blue square, red circle combination. So we're looking at blue-red combination. Well, if you take a look, here it is right here. There's the probability that any given person wins this game. Okay, theoretically, if some random person would play this game 18 times, they would win twice. Okay, or 1 out of every 9 times that they play. So then the question is, when you get to part C, so should Jerry and Marty play this game? What do you think? Would you play it? No, why not, Grace?
That's a ridiculously low.
Probability. There you go. Yep. And that's probably, I think, what most people would say. Like I said, 2 out of 18 reduced to 1 out of 9. Chances of you winning is only 1 out of every 9 times you play. And at $2 a game, you're going to spend, pretty much you're spending, on average, $18 to win a stuffed animal. Okay? You're going to spend $18, and maybe you win once. Hey, you might win more than once, but on average, you're only going to win 1 out of every 9 times. 8 out of 9, you're going to lose. Right? Or 16 out of 18, you're going to lose, is the idea. So, more than likely, I would say once you calculate the probabilities, probably not a great idea to play this game if you're playing because you want to absolutely win. Okay? Now, let me show you the difference here on this one. Go to the next page. This is going to take a whole lot less time, and in my opinion, is a whole lot easier. Okay? Notice it says, now draw a probability area model for the same exact game. I used the tree diagram because they said to. But in this case, if you had the option, and we haven't actually created the test at this point, but I'm going to tell you, you will have the option. You're not going to have to do a tree diagram or have to do an area model. You'll have the option of, here's the scenario, you figure out the answer, whichever way makes the most sense to you. But what I want you to notice on this one, we can use an area model because there's only 2 things that we're working with. Squares and circles. Which means we can go through and we can take that tree diagram and very, very quickly turn this into an area model. It's a 3x2 area model because you got 3 things that could happen in the first bag. You got 2 things that could happen in the second bag. And to me, and again, maybe you might be different. That's perfectly fine if it is. But in my mind, this makes more sense to me. This is more organized to me than a tree diagram is. Bag number 1, same exact idea. What do we have? Red, blue, or yellow? Bag number 2, what do we have? Yellow or red? And then once again, the corresponding probabilities of each thing happening. And so if we do that real quickly, 2, 6, 1, 6, and 3, 6. There, very, very quickly, you have your chart set up rather than your tree diagram. And now, same exact thing. You fill in the squares by multiplying the probabilities. It's the exact same thing that we just did. Okay? Like I said, to me, if I had the option, I would go area model every time that it's possible. Just because that seems more organized to me. If in your brain the tree diagram makes more sense, then do it that way. Okay? You can always use a tree diagram. You can't always use an area model. You got to go through and do it a little bit differently sometimes. Okay? Otherwise, I'm not even going to bother kind of finishing this because it's the same. At this point, it's the exact same thing. Okay? Multiply the fractions to find the different outcomes, and you're in the same spot we were at the end of the tree diagram. How we doing? Okay? Making some sense? Okay, so let's go on to one more problem then. Let's take a look at this basketball shooting problem. Alright, so shooting 1-and-1 free throws. A basketball player, Rimshot McGee, has a 70% free throw average. Okay, the opposing team is ahead by 1 point. Rimshot is at the foul line in a one-and-one situation. Okay, and just seconds left in the game. And just so for those people that are not real familiar with basketball, a 1-and-1 situation means a player shoots a free throw. If they make the shot, then they get a second shot. If they miss the first shot, they don't get a second shot at all. Okay, so that's what a 1-and-1 is in basketball. Again, if you're not real familiar. Make the first one, you get a second opportunity. Miss the first one, there is no second opportunity. Okay, that's it. So, first question here. First, take a guess. What do you think is the most likely outcome for Rimshot here? You think he's going to have 0 points, 1 point, or 2 points? What do you think is going to happen? Based on the fact that he's a 70% free throw shooter. What do you think? Ryan, what do you think? Give me your opinion here. Is he going to have 0, 1, or 2 points?
Probably 1 point.
1? Why do you say 1?
Because 70% is higher than 50, so the better chance he's going to get 1.
Okay, yeah, 70%. It's a pretty good chance that he's going to make one of them. Okay, hopefully it's at least the first one. Okay, if he misses the first one, well then he's in trouble. But I would say it's probably a pretty good guess. Okay, notice it says to draw a tree diagram to make the situation. We could do that. I'm not going to, but we could. Okay, instead I'm going to use the chart that they gave us right here, the area model. Okay, and kind of talk our way through that and explain it a little bit. So if you take a look at this one, notice first shot and second shot. That's why we can use an area model. There's only 2 things going on here. You only get up to 2 shots. In this area, that would be if he makes the first shot and then also makes the second shot. So we can multiply those 2 together to get the probability of making both of them, what's 7 times 7?
49.
49, which means 0.7 times 0.7, 0.49. Okay? So there is a 0.49 or 49% chance that he makes both of them. This area of the area model would be representing that he makes the first one but then misses the second one. Okay? 0.7 times 0.3. What's 7 times 3? 21, which means you put those decimals in, you get 0.21. There is a 21% chance that he makes the first one but then misses the second one. And finally, down here, quick question about this area model. Why is this line not extended? Why is it just one block? What's that? There it is. Because if you miss the first one, there is no second one. Okay? If you go ahead and you miss that first one, there is no second shot. So, first shot you miss, well, you don't have to worry about the probability of the second one. There is no probability of a second shot in this case. And so, plus if you take a look, by the way, let's say we added these two numbers up. 0.49 plus 0.21, what do we come up to? Yeah, 70%, which means there's your 30% that's left. 0.3. Or 0.30 if you want it as that. There's a 30% chance that he misses. Okay? Based on his free throw average is the idea. So now if we take a look, says Jeremy is working on a problem with Jenna. He remembers that the area model is sometimes useful. They set up the probability. Which parts of the model represent? We talked about that. How can we use this to calculate the probability that he gets exactly 1 point? And so we've kind of gone through. So now if we take a look at those probabilities of scoring 1 point, 2 points, or no points, what's the probability that he ends up with 1 point? That was kind of what we talked about before. What's the probability of 1 point? How many different ways here? We got three options, three things that can happen. How many of them does he end up in 1 point? What do you think? This one, 1 point or 2 points? Or 0?
2.
That one's 2, right? He made it, he made 2 makes. Okay, so that's 2 points. How about this one?
1.
Yeah, made the first one, missed the second one. How about this one? 0. There's your probabilities right there. Probability he ends up with 0 points is 30%. Probability that he ends up with 1 point is 21%. And the probability that he ends up with 2 points turns out to be 49%. So going back to what Ryan had said before, he said, I think you'll probably end up with 1 based on the 70%. Seemed logical at the time, right? Well, it actually turns out scoring 1 point has the lowest probability of happening out of the three options. There's only a 21% chance that he's going to have 1 point. The highest probability, almost a 50% chance he's going to make both, and 30% chance that he'll make that he won't end up with anything. Okay? So it turns out, based on probabilities, that in this case, even the instincts would tell you one thing, the probabilities actually tell you a little bit different. More than likely, he's going to end up with 2 points. Second option, he's going to end up with nothing. Okay? All right. I think I'm going to stop there. Just a quick heads up. I did put in the lesson, it's not in your lesson packet, but I did put in the lesson. This is basically, if you're struggling at all, this is a summary sheet. And these lessons, remember, are always out on Canvas, every one of these lessons. Here's a summary sheet of all the different probability models. Area model, tree diagram, basic probability it describes. This one sheet pretty much describes this week so far. Okay? And there's your practice to learn at this point. Now, we've still got about 10, 15 minutes left of class, so I'm not going to let you loose at this point. I'm not going to turn you loose and let you go. But with the last 10 minutes, if you have not done 421 yet, you should definitely be working on that. That's due today. If you haven't done 422, you should be working on that. 423 is the next one. Or the other option is, remember, the Delta Math is still out there as well. G29 is the Delta Math for this week. Okay, G29. You should get that done by the end of the week as well. Okay? And you got about, like I said, about 10, 15 minutes here to get some problems done, ask some questions if you need help, and we'll go from there. Okay?